EMOA and the Nickel Institute are both international industry associations who have wonderful resources to assist you with your decision making process. I'm a metallurgical engineer, material scientist, and consults on projects around the world. I am also the chair of ASTM E60 and on some of the ISO tags. This is an area where I'm very heavily involved, and I'm looking forward to sharing this information with you today. If you have questions as we go along, please post them. We will try to get to as many as we possibly can. And I'm going to dive in. Everything in this presentation is copyrighted. You need the permission from EMOA and the Nickel Institute if you're going to use it for some other purpose. The recording will be available for you to watch or for your colleagues to watch again. And we do hope you'll share the information with others. Everything I say today is a suggestion for your consideration. There are no recommendations being made. We are simply providing you with facts to assist you with your decision-making process. If anybody has just joined and they need either an AIA certificate or certificate of completion or credit, please look at the chat and follow the FlexMail link and fill out the form. I'm assuming that everyone has looked at the learning objectives when you signed up, but I'm going to give you a very high level overview. We're going to talk about the data and resources that are available to you, not just the basic sustainability information, but how to select an appropriate stainless steel for your application so that you get the desired longevity. And there will be a big focus on achieving longevity, not just with stainless steel, but stainless steel also helps extend the longevity of other materials. We'll talk about how stainless steel can specifically help you with whether it's lead points or meeting some of the IGCC requirements. Whenever you may be trying to achieve, we think that stainless steel can help you make your project more sustainable. And I'm going to point you to resources because I can only provide a quick overview in an hour. So we're going to first talk about some data and resources. If you go to the Team Stainless webpage, you will find the information I'm showing here. This is from what's posted currently is from a 2015 study that was done by Yale University. The International Stainless Steel Forum has regularly done assessments of stainless steel carbon footprint and production. These are all verified third-party studies from highly respected researchers. So, this is well-supported data collected on a global level. The 2019 publication is expected out in a few weeks, and I am going to share a few highlights from that. First, I want to point out that stainless steel is 100% recyclable into new stainless steel. There is no loss of properties. And we use as much recycled content as we possibly can in stainless steel. Because stainless steel production has grown at about 6% a year, as you can see in this graphic, and the typical service life, when you look at all applications, is about 20 years, you can see there's a significant gap between the growth and the scrap that's going to be available. So that maximum recycled content is limited by scrap availability. So we do use carbon steel scrap, to increase the total scrap content in stainless steel uh, because we want to maximize it. It reduces energy use and costs, and of course, reduces the carbon footprint. I'm showing 2015 data, and you can see the average recycled content around the world. I've noted that globally the average was 44%, 32% stainless steel, 12% carbon steel. In the US, it was 71%. But we have new data from a 2019 study that will be published shortly. The average recycled content in the United States is now up to 83%. And as you can see, that substantially reduced the carbon footprint of the stainless steel. Of course, the industry is doing other things to increase efficiency and reduce energy use so that we further improve our carbon footprint. There are some factors that we can't control, such as the availability of alternative energy, so that we can, reduce the carbon footprint associated with that. Additionally, there are many designs that are regularly used that make it hard to separate scrap and make that stainless steel or the carbon steel we use in recycling in our materials available. So we do encourage you as you design to consider whether or not you created a product where the materials can be separated and that scrap reused. This is 2015 end of life recycling rate data. And you can see then how much is collected for recycling, uh, and how much goes to a landfill. Uh, the biggest problem areas are things like household appliances and electronics and some of the metal goods, where we lose about 20% of the scrap because the metals aren't easily separated. That's true for some of building and construction applications too. Some curtain wall, for example, where the aluminum and stainless steel are being combined in a way where they can't be easily separated. Well, in other sectors like passenger vehicles, heavy industrial machinery, and others where we have large stainless steel focused applications, it's fairly easy to separate. We can't get to 100%. That's never going to happen. You're going to lose some small bits and pieces along the way. But as you can see, a very high percentage of the stainless steel is captured and recycled, and a lot of that's related to its high value. I did promise to provide some comparison of stainless steel with other architectural metals. As you can see, I put in the 83% recycled content for the United States and showed there were a 60 to 90% recapture rate that was shown on the prior slide. In comparison with carbon steel, it really depends on the type of product as to how much recycled content it will contain and what its recapture rate is. It is a lower value material. The large structural sections can also have a lot of recycled content, and they're very easy to capture and recycle. Well, sheet and strip may be limited to 25 to 35% recycled content. It really depends on the technology that's being used. For copper, electrical wire has to be pure virgin material. But other products can have 70 to 95% recycled content. Aluminum sheet, at least the aluminum sheet that is used on buildings, generally doesn't have recycled content. Um, Sometimes there is data published that averages the beverage cans in with other types of sheets, and it's important to make sure you're looking at the right information. Uh, Extrusions and castings can have a lot of recycled content, so that sheet that might have no recycled content can be used elsewhere. But I thought this might be helpful to understand um, the metals that you're using. ASTM E60 passed a new standard last year, E3199, which allows alternative allocation approaches for modeling recycling. Uh, so ISO only offers one approach, but there are other recognized valid approaches for doing calculations. And materials and how they are recycled vary a great deal. So we developed this so that a technically valid approach could be taken to calculating life cycle assessment. There are appendices for stainless steel, copper, gypsum, glass, plastics, cementous materials. We hope that there will be more soon, and I encourage you to take a look at the standard. Now I'm going to talk a bit about selecting materials for longevity. It's critical to understand the service environment. Whether we're talking about a high traffic indoor controlled environment hallway, which is going to have completely different wear and tear than an exterior application, whether it's the exterior of a building in a corrosive location or a bridge, whatever the application might be. But if you don't understand the environment, then you can't make appropriate metal decisions. This isn't just for stainless steel, it's true of all metals and materials. So, if something is fully, is sheltered versus fully exposed to precipitation, if it's sprayed or splashed with water or not, if there's pollution or the air is clean, all of those factors matter, as does salt exposure. I've listed some of the things that need to be considered. And I'm going to make a note for the structural engineers on this call that within AISC 370, in the commentary, we have listed some of the things that you need to consider as you are um, assessing an environment. And the data that you would need if you're speaking to a corrosion specialist like myself, so that we better understand what you need and can guide you. And I should note that you can get that guidance from the Nickel Institute and AMOA, the sponsors of this, but also from stainless steel producers and other industry associations that have that level of expertise on their staff. Here are two railing examples, one in New York City and one in the Canary Islands. I've talked to ma managers of parks around the world and in my travels, and every time I have those conversations, I'm consistently told that painted carbon steel railings that are painted every year usually structurally fail within 8 to 10 years. Um, it's a highly corrosive environment if you're going to have saltwater splashing. The railing in New York is 316, does have staining in a few locations where there's more splashing, but it was clearly an appropriate choice. This Canary Islands location is essentially a natural salt spray test. You can see the rocks below. They put up a demo railing in 316, and within a few weeks, it was badly stained. It was the wrong stainless steel for that location when they expected it to be pristine, not just structurally sound. So 2205 has performed very well. So it is a matter of always selecting the right material for the application. Um, Other metals have shorter service lives. They're less corrosion resistant. That doesn't mean you need to have stainless steel everywhere. It's a matter of using it in the right place. But there is a big difference in corrosion resistance. I have a picture that I took on Jin Mao where you could see the white corrosion product from the aluminum uh, all over the stainless steel. The stainless steel was fine. I have painted carbon steel and aluminum in some of these images, some of the failures I've seen over the years. You have to maintain other metals in corrosive environments to protect them from corrosion. Uh, the U.S. has done a series of studies, government funded, looking at the annual cost of metallic corrosion. The last study was done in 2002, so we're talking about 20-year-old data, but all of these studies have been consistent. They all show that we unfortunately are regularly specifying metals, and this is true of other materials, that are failing prematurely. And when this study was done, the annual cost was over $550 billion a year. Think about the carbon footprint associated with that. We could make a huge effort towards reducing the carbon footprint of our buildings and structures if we simply select the right material so that it lasts the life of that building or structure. If you look at another ASTM E60 standard, E2921, which is used in USGBC LEED, BREEAM, IGCC, it's the minimum criteria for comparing whole building life cycle assessment for use in codes, standards, and rating systems. Um, we spent a lot of years arguing about this as it was being developed, and set a 75-year service life. Both LEED and BREEAM have chosen to use a 60-year instead. But it was the first global specification for this purpose. And the basis of the calculation is that you have to take the life cycle inventory, and there is an NREL database for LCI, not as well populated as we might like, but it does exist. And you have to multiply that life cycle inventory by the number of replacements. So if you were using LEED, then it would be the number of replacements in 60 years. The cost of ownership should be considered too. So as we look at decarbonization, we are not considering how many replacements are going to be necessary, then we're really not looking at the full picture. There are many examples of reusing stainless steel. This is a building in the Pittsburgh area. It was completed in 1952, so it was a quite early stainless steel clad building, but this project was focused on the lobby. You can see that original 1952 stainless steel. It was dirty, it had some scratches, it had a number 4 finish on it. And then you look at the after pictures. That's the same stainless steel. There was a little bit that was replaced, but most of that is the same stainless steel It was just refinished, reshaped as necessary, and reused. I should also point out that stainless steel has zero emissions unless you put a coating on it. In this case, the building managers had been putting a coating on it to try to hide fingerprints rather than just cleaning. Um, Restoration of stainless steel is certainly possible so that you're not recladding. 150 East 42nd Street, or the Saccone Mobile Building, um, was really dirty. And the first cleaning out in 40 years restored the appearance. The Toronto Stock Exchange doors um, were restored and reused. There are many examples from uh, commercial kitchen equipment to doors and other applications. Stainless steel can provide very long life. I think that most of these applications are going to be familiar to many of you. And we can predict it. We have corrosion data from around the world. If there doesn't happen to be corrosion data from the location where your project is located, then there's probably data for similar enough climate so that we can predict how long it will last. And the same is true not just for stainless steel, but for other metals and materials. In this instance, I took the average corrosion rate, multiplied it by 30 years. And then I'm showing the SMACNA architectural sheet roof, typical roof thickness for each of these metals for a standard 16 3/4 inch wide standing seam panel. If the area is red, then we have lost enough metal so that there's a good chance that somewhere it has perforated. So we do know how it will perform in different environments. Different metals will perform. And I've seen, unfortunately, in my consulting some huge problems. This is a roof on a large complex in Jeddah in Saudi Arabia. The wrong stainless steel was selected. It was Type 316 was the wrong material for this location. A more corrosion-resistant stainless steel is needed. Now, when that roof was put in place, we didn't have this data. There have been a couple test sites in the Middle East that have collected data, but that site happened to be quite similar to this Dubai beach site. I didn't include the Type 316 data because in this location, Type 316 starts to exhibit staining quite quickly. I've consulted on projects in the Middle East where the staining was on the 316 was significant after a month of installation, and it wasn't contamination on the surface. You can see that other materials, and this is again a roofing comparison. You can see that other materials are corroding at such high rates that you could have failure within, a little over 2 years or perhaps as little as 16. So, the data is available. I've seen projects where roofs had failed before the building was even completed in some parts of the world. So it's important to look at this and to use the data so we obtain the longevity that we need and don't um, unnecessarily increase the carbon footprint of our buildings. We have great salt maps and pollution maps in the United States. This is the Australia chloride deposition map. Here's one for India. There's similar data for Europe. There is data to help guide you to determine how corrosive your location is. not for everywhere in the world, but there is quite a bit of data out there to assist. We also know a fair amount about de-icing salt, and there's a good article on de-icing salt that's widely referenced on AMOA's website, possibly on the Nickel Institute's too. I'm not sure. But it summarizes what research is out there, um, and I'm summarizing some of my personal experience too. This is an intersection outside of Chicago, and it was a multi-year study to show how far de-icing salt traveled, um, up to 1.2 miles. I personally documented it 2 miles from a roadway in a valley, and the only de-icing salt corrosion was at the top of a building in direct line with a highway. It was, well, from a corrosion perspective, fascinating. Was not very good from the architect's perspective. Um, it also rises quite high on buildings. The highest de-icing salt that am aware of in terms of documentation on a building in a big city is the 59th floor. It wasn't the stainless steel building. It was aluminum corrosion. But it doesn't really matter. If it can go that high on a building, you have to consider it. There are quite a few fascinating recent projects where buildings or other structures are being floated on water or put on piers. And, whether it's that kind of application or an industrial application, a lock and dam, a desalination plant, it's important to consider what's in that fluid, its pH, its chemistry, and select materials that are appropriate. We do have good data for that too. And you'll notice on this, sea and brackish water graph, there is no type 316. It's not a seawater grade stainless steel, despite the many posts to the contrary that you'll find online. When I had the opportunity to work on the Four Freedoms Memorial, which was one of the Franklin D. Roosevelt memorials in the United States, um, I was told we had a 100-year storm surge design requirement. So I asked, well, how high would the water go, and how long will the railings and the anchoring for the stone be immersed? And I was told that everything would be immersed and that it could be days at minimum. And so we used 2205. There was a desire not to do maintenance. Um, and some of the stainless steel just wouldn't be accessible. So, unfortunately, within a few weeks of the grand opening, Superstorm Sandy came through and immersed everything. There was no corrosion on the 2205. So it did meet that requirement. Well, many 316 railings throughout New York City were pretty badly stained. I do want to point out some resources. On AMOA's website, which I have pictured here, you can see that there is a stainless steel selection system. And within that area of the website, we also have specific pages on galvanic corrosion, site evaluation, coastal and de-icing salt, and soil exposure, other things you should consider. There are two brochures in particular that I suggest. Um, First, Guidelines for Corrosion Prevention is a much thicker brochure that provides a lot more detail. Which stainless steel should be specified for exterior applications is a scoring system. So it's a much higher level point system to guide you through that process. now going to focus briefly on how stainless steel can help to reduce energy requirements for buildings. Um, First of all, roofs and the material you choose for roofs and the finish are critical in terms of avoiding heat gain. I love the Pittsburgh Convention Center example, not because I live in Pittsburgh, which I do, but because when this was built, um, it we didn't have the data to select an appropriate metal for the roof that would help reduce energy use. Most buildings, when they're recertified, end up going from maybe gold to silver. They go down rather than up. Um, this building did the opposite. That large sloping roof um, in stainless steel um, had did not deteriorate in terms of its SRI value, which wasn't part of the equation when it was built, but it went from gold to platinum. It uses 29% less energy than was expected because of the roof choice. So, of course, roof slope matters in these calculations, but with bare stainless steel, the solar reflective index varies from 39 to 60 uh, in the typical finishes that might be used for a roof. Um, so for a steep slope roof, it meets the requirements and it doesn't lose that SRI value over time unless you've used a stainless steel that's going to corrode in the environment. Any metal with a white coating, you can get to scores of over 100. And yes, you can paint stainless steel. It's done far more frequently in Asia, particularly in Japan, than we do here. Um, Many materials we use for roofing have quite low SRI values and they add to heat gain. Vegetated roofs are, of course, a wonderful way to reduce building energy consumption. But you have to consider that a vegetated roof and even organic fertilizers are corrosive. It's a soil environment. That plastic liner is not going to last forever, and you probably don't want to, um, you know, have to replace it on a regular basis, and you wouldn't necessarily know it had deteriorated until you have a perforation in the roof, and perforations have happened. 316L is generally the minimum that you should consider specifying. Welded seam roofs are used for these applications for planters. Um, and and it is a good choice if you really want a long-lasting vegetated roof. There is data on performance of stainless steel and other metals in soil environments. I'm simply making you aware of it. I'm not going to delve into the details, but stainless steel performs much better than other common metals. Aluminum and carbon steel really are not suitable for being in soil. One of the next present webinar that I'm going to give is going to be on sunscreens. So I'm going to simply mention that there are wonderful resources for fenestration energy modeling. I'm going to delve into ComFen in that presentation and how it can be used. But stainless steel is a long-lasting material choice. Uh, the finish is not going to deteriorate, as I already mentioned, if you've selected an appropriate finish. This is a building where sunscreens and woven stainless steel were put on part of the building. And you can see that the shading really made a significant difference in temperature. And that then helped to reduce the building temperature. So I'm going to encourage you to join us for that presentation too. So let's talk about avoiding indoor emissions and water quality and some of the other characteristics that you're going to want to consider. First of all, stainless steel has no VOCs. It's used in buildings where emissions are not permissible. Unless you choose to put a coating on it, it will make zero contribution to VOCs. Stainless steel also can help by having grates at doors so that you're minimizing the contaminants being brought into the building and not having a corrosion issue. You can clean stainless steel in public bathrooms and in similar high traffic locations simply with steam and kill the bacteria rather than using potentially problematic chemicals. You can also use termite mesh made out of stainless steel to provide a permanent barrier to eliminate pesticide use. So here is I'm sorry, that one slide wasn't showing up particularly well, but this is the percentage of bacteria retained on stainless steel after a 10-second wipe on an abraded surface of stainless steel versus enamel steel, mineral resin, etc. So there's a good reason why stainless steel is used in commercial kitchens. This is stainless steel termite mesh. You can get a substantial discount with your insurance company if you use it too, at least in some parts of the United States. I did want to mention another ASTM standard, E3182. This is an alternative to the HPDs. It is, you know, it's focused on the actual risk, not whether or not there might be a hazard. Um, there are many things that could be a hazard, but is there really a risk of that occurring in your project? And so this does, we think provide a very logical way of assessing materials, building products to determine if they present a risk and documenting that. Um, I'm showing runoff from a variety of different roof materials. Um, these all are metals that can be biocides or otherwise, something you don't want to have in water that you might be collecting and then putting onto other plants. Or if you are in an area where the groundwater is horrible, potentially using for potable water, which is unfortunately is the case in areas where potable water is limited. This is from a study that was done in Sweden. Um, it compared 304, and this is a coastal location where we generally would use 304, but with that, the runoff levels were either below detectable limits or well below typical drinking water levels. So if you wanting to capture water uh, for use, whether it's for potable applications or for watering plants from your roof, then you might want to consider stainless steel. It's also used for stainless steel water lines and tanks, connections to the mains. It's particularly advantageous if you are in an area where there's seismic conditions and water line failures could occur, or the soils are particularly corrosive if it's underground line. So there are many reasons, and the Nickel Institute has a number of brochures on this topic. Extending the life of building materials is another area where stainless steel can provide a great deal of of, of help. Um, because if we can, we do want to extend the life of all the materials used on a building. Um, Stainless steel is mandated by code in some countries. Unfortunately, not here at this point. I'm showing an image of a a masonry wall that failed because the galvanized wall ties corroded away, and there was nothing to hold it in place. And during a seismic event, walls fell. You don't have to have a seismic event for masonry or stone to start falling off of buildings, unfortunately. It's been a significant issue um, in, in North America and other parts of the world. But you can use stainless steel during your new construction, and there are many products for retrofits to hold the masonry in place, again, using stainless steel. The U.S. Federal Emergency Management Association they recommend, not me, stainless steel wire to hold tile in place if you were in a high wind area. And it's something to consider anyway, even if you're not in a high wind area, because corrosion of other types of wire can cause your roof to fail prematurely. The concern here is that tile can become a very dangerous flying projectile. Another example of extending materials, the Golden Gate Bridge will be using 2205 duplex stainless steel for its seismic retrofit after an extensive investigation. And I'm showing on this slide um, a the stress strain curve taken all the way out to failure. The area under the curve is how much energy can be absorbed by that metal. It's critical for seismic design, blast, and impact toughness. So yes, I am bringing in resilience into the picture. Ideally, we want things to be both sustainable and resilient. As you can see, the area under the curve, especially for the austenitic stainless steels, but also the duplexes, is substantially larger than for carbon steel or for aluminum. The Statue of Liberty is another example of restoration using stainless steel. To my knowledge, this was the first structural application for duplex stainless steel in a large structural application in a structure that was not industrial in the United States, perhaps globally. Um, all of that framing going from the core out to the copper skin is duplex stainless steel. The armature bars are 316 now. It used to all be iron because of its corrosion resistance and because it matches the coefficient of thermal expansion of copper. The Sydney Opera House originally had carbon steel rebar, which, as you can see from this picture I took, I happened to be here when they were doing some of the work on it, that there were pieces corroded away. They replaced that with stainless steel rebar to save the Sydney Opera House. It's too bad it wasn't done at the beginning. Ideally, we want materials that are going to be both sustainable and resilient. Um, if you have a design, if you have a roof that's able to stay on your building, then it's likely to save the rest of the building. And I've seen a number of images of the one lone stainless steel roofed house surviving um, as hurricanes have come through. What does resilience mean? Well, it actually has been defined. There is a new ASTM E60 standard which was the first international standard to define resilience and resilient design. There's also an ASTM E54 Homeland Security standard that was also passed last year that is specific to assessing communities and for resilience. So there are some wonderful resources out there, but we're talking about the ability to resist natural and human caused events, whatever they might be. And we certainly need to consider coastal flooding and whether materials can withstand it. It might not be part of your normal consideration as you design a building, but in coastal areas, we really have to, if we look at the projections for what's going to happen in terms of sea level rise. Fires also have to be considered. We've seen some pretty horrific building fires in recent years. That was a tunnel fire, which is a bit different. But there is a lot of data out there in applications where the fire temperature is lower. Typically not an industrial building, but it could be a building for other purposes. You can see that the austenitic stainless steels retain their strength as you get to higher temperatures better than carbon steel, much less aluminum, which doesn't retain its strength at all. Here's the stiffness retention. This is part of why both, this fire performance and the energy absorption, why we're seeing more and more stainless steel being used for framing for glass curtain wall, because it can withstand blasts and fires and impact and all that might happen. I want to point you towards some resources. On AMOA's webpage, we have a 550 PDF stainless steel library that was developed by both the Nickel Institute and AMOA. An extensive number of technical resource pages on a whole variety of different products and applications related to building construction. I also want to make you aware of the fantastic technical help that can be obtained through the Nickel Institute. And of course, there are many resources on their website too. Please do check out their websites if you're not familiar. In conclusion, stainless steel is a high recycled content material, and we do not lose properties. It's not downcycled. You can create the same high quality material over and over again. It's diverted from landfills. Its value is too high, and to end up in a landfill unless the design doesn't allow separation of the materials. It's capable of meeting at least a 75-year life. The alloying elements are encapsulated. There are no VOCs. It can help extend the life of other materials. It's regularly reused during renovations. So there are many benefits. And with that, we're happy to answer questions.
Okay. There have been a few questions that have come in through LinkedIn Live already. I'm just going to go ahead and read those off. If you're viewing on LinkedIn Live, just be aware that there is a little bit of a delay between Zoom and LinkedIn Live. So if there is going to be a clarification, just bear with that. Okay, first question is, can you please provide any comment or briefing about the sustainability and resilience, or just in general about the Doha airport roofing? Are you familiar?
I am very familiar with the Doha Airport roof. I did some consulting on the Doha Airport roof. So, there were different stainless steels used on different buildings. Um, the main terminal, used a stainless steel that's a bit more corrosion resistant than 316. And then some of the auxiliary buildings used 2205, which was another step up in corrosion resistance. So there were different duplex alloys with different levels of corrosion resistance used. I should note that the project um, only assumed a 10-year life. So it was a much shorter life than typical. And I did see during my inspection, I did see some very light pitting corrosion on the lower alloyed duplex stainless steel while the project was still under construction. Separate from that, there were some contamination issues with iron contamination, which had to be addressed, which was causing some staining. I know that the report was shared pretty broadly by the airport authority, so I feel comfortable saying that. I'm not aware, I have not looked at the buildings since then, but in that, the data that I showed for um, previously in the presentation, I might be able to get back to it. Did would be relevant for this location. It's the same type of very high salt accumulation, very high dust accumulation right on the water during the evening hours. The humidity is high. So there's the salt accumulations are quite adherent. And that's part of the problem. So even with 2205, we weren't talking about a 100-year design life, without staining. I mean, which was the issue. But it's certainly much better than other materials that could have been used. I hope that answers the question.
Um, yeah, here, sorry, I'm just looking down here. There's quite a few questions, actually. This is great. I'm just kind of going to go in chronological order. Similarly, can you provide a comment about the sustainability and or resilience of hangar doors on ocean-going vessels? Are you familiar with that at all?
Sure. I mean, it would really depend on what they're made out of. Um, they doors like that, I mean, can be made from a variety of different stainless steels. Sometimes assumptions are made about cleaning, or they may not care about about that. But in any case, it really depends on what it's exposed to. Other than the ocean itself, as to what stainless steel might be appropriate. I need more information would be needed.
Okay, thank you very much, Catherine. Um, Next question is, do you happen to know the level of LEED certification for the, excuse me, the Pittsburgh Convention Center roof that you discussed in the,
It's
um,
platinum.
is platinum? Okay.
It went from gold to platinum. And the
Okay.
building, that's for the building itself, not just the roof, because the it's always an overall assessment of the building, its energy use, its water use, etc. And it was an existing building recertification that took it to platinum. It was, by the way, the world's first sustainably designed convention center.
Oh, very cool to have that here in Pittsburgh. I'm also there myself. We had another question for any of the projects that you spoke about that used type 316L stainless steel as a significant portion of the project. Do you feel that any of those could have or should have been other alloys of stainless steel, perhaps more highly alloyed grades, or even the other direction?
Um, I would rather, because I consult on buildings where I'm often signing NDAs. I prefer not to speak about a specific project and may not be allowed to, but I would say that the the bigger architecture firms or those that know more about stainless steel are generally using type 316 for exterior applications on buildings. In the United States, 60% of our population is coastal, and that's true of everywhere in the world. That's the global average. And then, we have 70% of our population that is in an area where de-icing is occurring, and the salts can reach roofs. It depends on the height of the roof, of course, but and certainly can enrich wall panels. So I think 316 is often the minimum that is being considered by these architecture firms because they have run into problems. Now, that's not saying that there aren't applications where 304 is just fine. If you're not near, you're not near the coast, you're not near a highway or a busy road, then 304 can be great. But I've seen a lot more specification across the board of 316 to avoid problems because there's often an aesthetic requirement and staining is just not acceptable. I have certainly seen projects or parts of projects where I don't think 316 was enough. I've consulted on several where I advised the use of 2205 for the lowest floors, simply because of the salt exposure and the location being sheltered and knowing that there wasn't going to be regular cleaning, or because there was insistence on a very rough finish. I've unfortunately seen quite a few type 316 projects with rough finishes in areas with de-icing that were pretty badly stained by spring. So that really should be considered. So I guess I see more under specification rather than over specification. Not that they both can't happen.
Thank you. And somewhat related to that, is type 316 preferred within a kilometer radius of a coastal environment? And I know you kind of just spoke about the finish implications as well.
Right. And I actually it's generally a lot more than a kilometer. And I'm going to see if I can quickly go back to the salt mapping, which is way at the beginning. Let's see if I can do that, because I think that's critical to understand. So, and I can show you the Australian map too, and maybe I should. On the Australian map, red is the worst area, and in yellow there's still quite a bit of salt. In the U.S., everything that's in that a shade of orange category is a significant amount of salt deposition. And I think the US is was the first country to regularly combine both wet and dry deposition of salt, which gives us a much more complete picture of what's actually happening. And as you can see, a kilometer inland would not be enough in most places in the United States. There sometimes you have to be 50, 60 miles inland or even further um, before 304 would be a viable choice, especially if it's not going to be cleaned and staining is not permissible. I should note that the wood industry has changed their standards. And for wood decks, and of course, treated lumber is corrosive to begin with, but wherever any of these orange areas, they have gone to recommending type 316 stainless steel and 304 elsewhere where there's lower salt exposure because the decks were failing prematurely because of the galvanized fasteners. And that's something they're changing in code. So, there's a good reason to look at this type of data as you're making decisions. And of course, this doesn't show the de-icing salts. And, we have data, there's, corrosion maps for India too. Um, certainly those red areas are not all right by the coast. So yeah, it's important to find the data and look at it, or speak to someone who has access to it as you're making material decisions, not just for stainless steel.
Thank you, Catherine. Um, okay, another question we have is, does steel produced using a quote green method, such as an electric arc furnace or a hydrogen-based direct reduced iron method, have the same or better quality over conventionally produced steels?
Um, well, in stainless steel production, we are of course using you know, AODs we're able to remove a lot more impurities. And the ability to remove impurities can also then allow the use of scrap that might not otherwise be usable. Some of the data that I shared for different carbon steel products versus stainless steel, it really is, about how many impurities can be removed based on the technology that they have. So, it's probably I probably shouldn't delve too much more into that. So I'll leave it. There's certainly information readily available about those differences in production.
Thank you, Catherine. Another question. Can you explain a little bit about standing seam roofing and any of the differences between different commonly used grades of stainless steel for those systems?
Well, stainless steel can be used for any of the common architectural metal roofing methods. So I should note that if with a, at least an austenitic stainless steel, because of its formability, can certainly be used for any standard type of metal roofing. With a duplex stainless steel, because of its higher strength, the designs have to be modified. So for some of the roofing applications where 2205 has been, or other duplexes have been used, I worked on a project where 2507 was used with color. Really a fascinating project. But in any case, if you with a duplex, you'd have to modify because the design, because you can't make the tight bends as you can with an austenitic. That's true for ferritic roofing as well.
Thank you. That kind of leads somewhat nicely into the next question is, can you speak a little bit about some of the fabrication differences between these commonly used austenitics and um, they wrote 2205 duplex, but I'm assuming they mean duplexes in general.
Sure, and being they're the duplexes are certainly stronger. You can't form as tight a bend. Uh, and I think perhaps rather than my trying to delve into that in detail, I'm going to point everyone toward the wonderful brochures that have been developed on fabrication of the austenitic and duplex stainless steels, which do have comparisons. Um, I think that would be, rather than my making more general comments, probably a better way of directing our audience, because those go into that topic much more substantially than the simple commentary about how the strength and how tight a radius you can form without problem. And there are differences in spring back too.
You, Catherine, I think we just have maybe one or two more questions here. Um, let's see, the last question is about load-bearing members used in seismic conditions. Do you have any suggestions for consideration about what would be grades that all alloys that offer good resilience and for load-bearing members in seismic areas?
Um, Generally, if you're going to have a great deal of seismic loading or cyclical loading, the austenitics are a step better than the duplexes. I mean, a significant step better. But it really depends on the design as to which is likely to be better. Um, so that you have to it's really more of a structural assessment looking at the characteristics of each um, and what you need and characteristics you need, whether you can capitalize on the higher strength of the duplexes and whether thinner sections are are more important. But many of the seismic retrofit applications do use austenitic stainless steels because of their higher energy absorption. Of course, I showed an example of the Golden Gate Bridge where 2205 was used, but that was heavily driven by the the corrosiveness of that location and the need for higher strength. So it really will be dependent on the specifics of a particular design.
Okay, thank you. One more question just came in. Um, again, and maybe you want to talk about this from the sustainability and resilience perspective, but they asked about stress corrosion cracking and its prevention.
Well, there is, again, we have some great literature on that. I believe that most comprehensive tables are in the Nickel Institute brochure on high performance, I think it's high performance stainless steels is the name of the brochure. But again, this is a matter of selecting the right stainless steel for the application. The duplexes are going to be better than the austenitic. And you know, if you're talking about an indoor swimming pool application at ceiling level or something that's highly loaded, that's exterior in a salt laden environment, then I mean this is something you really should be considering. I mean, there have been a range of different failures that have occurred in different interior and exterior environments. For example, 316 got used for highly loaded structural applications on a glass curtain wall in the Middle East, on the coast. This, the same type of environment. I can't name I can't name the location, but it was a very severe coastal environment, and within a short period of time, it failed due to stress corrosion cracking, and you can imagine how horrifying that would be to have a glass curtain wall falling down. So yes, it is. There are exterior applications. It's not just a swimming pool issue where chloride stress corrosion cracking can happen. You need to look at how heavily loaded it is and what it's exposed to. And we have some great literature on that, and can direct you to people who are have tremendous expertise in this area.
Thank you. I'm not seeing any more questions. If anyone would like to post a last minute question, like in the next 90 seconds, go ahead. Otherwise, a lot of people are asking about the recording. If you're watching through LinkedIn Live, it will actually remain, the video will remain there as a recording where you can watch it whenever you want. Just go in through that same link and that event. And for everyone watching here on Zoom, in just a minute here, I will put that link for you into the chat. If you have any questions, any other follow-up questions, I'm also going to be putting my email in both chats, and feel free to direct your questions towards me, and I will get back to you. Thank you so much. This has been another wonderful question and answer presentation. And thank you so much, Catherine. This was incredibly informative and really interesting to listen to. So thank you again.
Well, thank you, Carly, and thank you everyone for joining us today.
Okay. I believe that is the end of the questions. So thank you again. I will post that link here for the Zoom people, and then we will sign off. Have a great rest of your day.